stop by.
For the sombrero?
Yes, for humor.
Do you guys remember who assigns a letter grade to your main field this semester? So you guys check this out. In both these scenarios, I need to exert a force of 100 pounds to push my car to get it moving. Same thing down here. But in the first case scenario, I'm only moving the car 10 feet. In the second case scenario, I move my car 100 feet. Now listen carefully to my choice of words. In which one of the pictures, the top or the bottom, do I need to exert a greater force? I think neither. I exerted the same darn force, 100 pounds, to get the car moving. But am I not going to be more perspired or more tired in the second case scenario? I should be. See, guys, there's no theory here. There's no theory. I just want to make up a man-made definition of a word that describes how these two scenarios are different. And what I'm going to do mathematically or arithmetically speaking is distinguish these two scenarios by saying in the first case, if I took the force and multiplied by the distance, or down here it took the force and multiplied by the distance, I get different numbers. In the second case scenario, it's a bigger number in the first case scenario. And I think playing this little game of multiplication separates these two scenarios. And I got a new name for this. I call it work. Man-made definition. I think work is going to be interpreted or defined to be the force exerted on an object to get it moving times the distance for which I needed to travel. And you have to appreciate the fact that with this man-made definition, it does seem to do the job of separating these two scenarios. So I am not with my pen proving any theorem. It's just a man-made definition. Work will be interpreted as force times distance. So you let me take a peek at some nifty little examples. There are a lot of us in this room who are not using our textbook. Personally, I don't look carefully at our textbook. And so you guys, I apologize for this, but I have a tendency not to address a lot of these issues by using some funky new technique, which a lot of these textbooks seem to do. Personally, I stick to my Math B ways. And if I want to draw a coordinate axis system, I will typically draw the x-axis in the horizontal direction. And the positive x-axis goes to the right, like you usually have it in algebra. And here's my y-axis. And I just kind of maintain that. So let me make up an example out of thin air. I got a water tank. Looks like this. Where the outside boundary, if you don't mind me saying it this way, is parabolic, mathematically modeled with the equation y equals x squared. But it's in free space. And the dimensions of this tank are going to be, how about 10 meters this direction? Oh, by the way, can I put a little spout on top? And the spout reaches above the tank by, I don't know, how about 2 meters? And let's suppose the tank is not completely full. Let's suppose the tank is only filled up to the point where I'm 5 meters from the top. You guys, I'm making these numbers up out of thin air. So question, how much work is required to pump this water out through the spout and out of the tank? And I think to do that, I will draw in a Cartesian coordinate system. How about with my green pen? I'll place it at the bottom, my x-axis that is to say, and my y-axis will run straight through symmetrically to the top. I kind of like my axes there because if I need to talk about the boundary curve of the parabola, its equation has no translation involved. It's merely y equals x squared. Whereas if I put my x-axis up here, that's just fine. It's just that now it's not going to be the equation y equals x squared, but y equals x squared minus some constant. I have to figure out what it is. So again, I'm just being lazy with my x-axis where it is. So the equation, boundary curve, is a nice equation. Next, I want to talk about an arbitrary horizontal sliver of water. In other words, if you guys allow me to draw in here, this sliver of water. The first thing I do is I take a peek at the volume of that ice sliver of water and try to compute it. To do that, if you guys don't mind, can I think of a point on the boundary right here as being x sub I comma y sub I? But when it comes to that small red sliver of water, geometrically speaking, using my high school geometry language, I think it's just a right circular cylinder. And a right circular cylinder has a volume that can be computed by the area of the base times the height. But the area of the base is nothing more than pi times the radius of an ice sliver of water times its height, which is a small direction or dimension, in the y direction. You guys, with my green pen, is that too sloppy? I didn't label the vertical axis. But I told you out loud, I got traditional labeling. Wise up. Oh, you know what? This isn't going to work. You guys know darn well eventually I'm going to transform this delta y into a dy when I take the limit of Riemann sum. So if you guys don't mind, can I go back to the picture? When it comes to the radius of this red sliver, what would that radius be in terms of x and or y's? But for an arbitrary sliver, what's the radius of this red circle? I think it's just x of I. Oh, are you saying I forgot to square it? My apologies. You guys, it still isn't going to work. Look, I said I'm going to eventually turn this into a dy. I still have x's. Let's take it one step further. I got pi times x of y squared times delta y. Oh, let's play this game. This boundary curve has this equation. So hear me. With that relationship down there, what's another name for x of y squared?
Root y.
I think y is a y period. Do you guys agree? And again, can I impress upon you, I'm being so darn lazy, I'm just looking at my picture, identifying things. Next. I want you guys to help me generate an expression that identifies how much force I need to exert with my fingertip underneath this red sliver of water just to get it moving upwards. Now, I think the force I need to exert to get this object moving upwards is going to be nothing more than it's, anybody?
Opposite of gravity.
What's that?
Gravity.
I have to incorporate that. I agree. So I think that force is going to be nothing more than mass times acceleration. So the force to get things moving upwards is just mass times acceleration. Can I refer to acceleration as g? Because I like g for the
Gravity.
Constant for gravity. By the way, mass can be computed by looking at density times volume of that ice sliver times gravity.
That's just dirty math.
Okay, it's dirty math. Actually, it's going to get more dirty in a second because I'm going to put numbers for rho and g. What's the density of water? Does anybody know? 1,000 kilograms per cubic meters, yes. And if you didn't know that, don't worry about it. Now you do.
So,
Yes.
will you tell us that on a test?
No, because now you know it. And the gravitational pull for this particular planet is approximately 9.8 meters per second squared, or if you prefer British units, it would be 32, approximately 32 feet per centimeter second squared. You guys, I'm nervous. I'm a mathematician. I will argue to the end that using these metric units for international units is so superior. It's just that since I'm officially teaching out of this book, it's all this author uses. For that reason, I'm going to stick to just international units, okay? Oh, I forgot the volume. How do I come up with that?
In the grade?
I've already done it.
Yeah.
Right there. It's just pi times y sub I times delta y. Now, I think the work required to get the ice sliver of water up and out that spout is going to be nothing more than the product of the force needed to exert in getting it moving times the distance to get the ice sliver up and out that spout. Well, you know what? I've already got the force. It's 100. Excuse me, I misspoke. 1,000 times 9.8 times my pi times y sub I delta y. I just need to multiply the distance for which I need to travel that ice sliver to get out that spout.
Doesn't that gravity
You know, it does need to be negative, but I'm going to be really careful to say, I'm going to stand here and throw a ball in the upward direction with initial velocity v sub naught as possible. Then I need to interpret that gravity is negative, or that acceleration, I should say, is negative. But since here, I'm not really talking about that direction in terms of throwing things, I just want to put the constant in terms of passing value. And I think the distance it needs to travel, you guys watch again how lazy I am. If I project this point onto the y-axis with my blue pen, where am I located on my vertical y-axis? Y sub I. And when you take a peek at the top of the spout, where are the y-axis at located? Well, I think it's just constant. What's this height? What's this constant from here, the bottom to the top of the tank? I'll put the pen.
Delta Y.
I'll sit down.
Y sub I plus 5.
Guys, my math students can answer this question just like that.
X plus 7.
Say it again.
Or Y plus 7.
Say it one more time.
Y sub I plus 5.
What's the height of the tank? Well, if this is 10, well, I think I did implicitly. If the diameter of the top is 10 meters, half that's going to be 5 meters. But that means the point up here has an x coordinate of 5. So y coordinate is going to be 25. You okay with that? Okay, now that we revisit our math D, I guess this tick's located at 27. I heard that. The height of the tank? Oh, but 2 meters above it. So help me with this. Is it not true that this would represent the distance that ice sliver would have to travel to get to the very top spout to spew out that hole? That's what you say, yes.
Absolutely.
Oh, thank you goodness. All right. And if you guys agree, I guess I'm done then. Well, not quite, but close to being done. I guess my D sub I is at 27, did I say? Is that minus Y sub I in my picture? Aw, you guys, I did blow it. Shoot. I've addressed an issue or addressed a question. What kind of amount of work is required to get that ice sliver up and out that spout? That's not my question. My original question is, how much work is required to pump all the water out of the tank in this fashion? Well, then I think I need to take the W spies, sum them together, and take the limit as n increase up bound, where n is how many subdivisions I have on the vertical axis. And so I think that's going to transform the total work to be nothing more than the definite integral of my 9,800 times pi times 27y minus y squared dy. Let's just deal with the bounds of integration. I said, let's deal with the bounds of integration. I can say that sometimes. 20. I heard that. Remember how my fluid wasn't filling up the tank completely? The water was up to 5 meters below the top level. Come on, you guys. Here's time to shake me up. This is the big deal. And by the way, I'm not going to finish my question if that's okay. I mean, you can integrate, right? Wouldn't it be better for me to spend time in class today just setting up these integrals?
Yes.
Okay. You know what? I think I skipped something. I did not mean to. I really did mess this up in my head. Because I'm using international units, what's force measured? Newtons. Distance can be measured in anything in Darwin, please. Let's do something standard. Let's call it meters. So I think in the end, this is a number measured in Newton meters. Oh, you know what? This sounds complex, doesn't it? I guess we got a nicer name for Newton meters, namely
Joules.
Joules. Good. I agree.
How did you get the limit of integration?
Here's how he did it. Now remember, I really didn't have this tank completely filled. It was filled to a position or a height that was 5 meters below the top. And I think the top is going to be, where the height is going to be 25 meters. And so I need you to take a peek at where all these slivers live of where the water is before I pump anything out. And I think when you stack up all these slivers of water that are red, I think they stack from a low extreme y value 0 up to a positive extreme y value positive 20. So I'm really looking at the stacking of those red slivers.
Oh, just a quick question. The book just uses J to abbreviate joules.
Of course, an uppercase J is traditional.
Okay.
Or you can say Newton meters, that's fine too.
Okay.
They're synonymous.
So, how did you get the height of the tank? I still don't see where you got 25.
I was being this lazy. I said, well, you know, the top of this tank actually has a diameter of 10 meters.